a few more things about the structure of compact Lie groups, which is needed before we can really embark on talking about representation theory. Okay, I make a number of statements, mostly without proofs, and the best proofs are usually via topology and differential geometry. So,
with yellow chalks.
sorry?
With yellow.
Yeah. But I was the one who recommended that first. And I was happy to see that great sense. Anyway. Okay, so G is a compact Lie group. Compact connected Lie group. Now, some of these statements will work for a non-connected group also, but by and large, compact connected groups are the things which are most interesting. And in any case, some of you want to know for compact connected groups, you can easily see what to do for groups that are not connected. The identically connected component is a connected compact group whose the quotient by that is a finite group. So using that, one can say a lot about general representations. Sometimes it can be quite complicated and not so easy to handle, but by and large, you can make many statements which are essentially easily deduced from what we know about compact groups, compact connected groups. So G is a compact connected group. G is abelian. G is isomorphic as a topological group, the product of circles, some finite number of copies. Here, S1. Actually, one denotes if there are n copies, finite number, say n copies, it's also denoted Tn. So S1, n, if you write it, it will be more complicated. You can't write Sn because Sn usually means n-dimensional sphere. So anyway, Tn is the it's finite number of n copies is denoted also Tn, and this is G is abelian. It's a standard result. Not difficult to prove. I won't go into it. G is connected abelian, of course. But the bracket assumption G is always compact connected. If G is abelian, it's isomorphic to n-dimensional torus. Secondly, if you take G compact and any point x in G, there is a tonal subgroup of G containing x, or more generally, if T in G is a torus and x in G commutes with the torus, with all elements of the torus, then there is a torus T prime in G containing T and x. The best way of proving this is to use differential geometry. The first statement that through any x there is the torus is proved by the following method. First, you prove that you take the compact group, it carries a bi-invariant Riemannian metric, and it turns out that geodesics for the bi-invariant metric through the identity are simply one-parameter subgroups, which means that exponential images of the you take the exponential image, you get a connected one-parameter group, which means the image of R, so you get a connected subgroup. You take its closure, you get a connected compact group, and that's a torus. So any point x is contained in the torus. This is one method of proof. There are other methods of proof which are in some sense more interesting, using more topology. There is the theorem of Hopf, which describes the cohomology algebra of G. which is turns out to be the exterior algebra of some finite number of generators. And using that, you can prove that the mapping x going to x power r of G into itself has positive degree, and therefore it's projected. So every element you can extract R root. So you extract R root, then extract what you get is extract a further R root and so on. Say square root. First extract the square root, then the fourth root, and go on, take it. And you get a countable group and take its torsion. And you can easily show that torsion is a connected compact group, and that you can prove from that to another method. And you can adapt that method for the second statement also. The second statement, so next, third statement, first, any x in G is contained, this is the definition of this statement in the maximal torus. Maximal torus of group of G. This is the definition of the first statement. Because any torus is going to be contained in the maximal torus, because the finite dimensional situation, you look at the Lie algebras, and increasing sequence of Lie algebras, abelian Lie algebras is going to terminate. So if you have a torus, take its Lie algebra, if you have an increasing family of torus, it has to terminate. From that, it's clear that it's going to be maximal torus. Maximal torus of group of G. All maximal tori are maximal abelians of groups. Of G. Maximal torus, of course, if you want to make the condition maximal connected abelian, of course, maximal torus is maximal. But the point is, if you have a maximal torus and take a point outside which commutes with it, it automatically belongs to the torus. That's what it means to say it's maximal abelian. And that follows from the second statement. Take this maximal torus, take an element which commutes with it, together they will be inside another torus, which means the original torus, because the original torus was maximal. So, and finally, this is the most important statement we need. Every element so all maximal tori are usually conjugate. Maximal tori in G are mutually conjugate. Tori is simply product of circles. So one understands their representations quite well. And for one thing, they are abelian. To take any irreducible representation, it's necessarily one dimensional. And therefore is given by a character. So the character group is the same as a set of all inequivalent irreducible representations. Usually inequivalent irreducible representations. The character group. So one understands the representations of the torus. One hopes to be able to, from that beginning, try to get all representations of G. What you do is start with the representation of G, restrict it to G, and analyze it. That's the way it should be done. But the best it turns out that from technical point of view, it's better to talk of representation of Lie algebras than Lie groups. So in that context, so one knows, you know that for a compact group, every representation is completely reducible, and therefore a direct sum of irreducible representations. So what we would like to know is how to classify irreducible representations compact. Now, and we also know that all those are finite dimensional. So if rho from G to G and B is a finite dimensional representation, one knows from Lie theory, it induces a representation which I call rho dot of the Lie algebra of G G2. G or B is the same thing as grade 0. Sorry, it's the same thing as all grades with the bracket operation. So it induces the representation of G on the same vector space. And rho dot determines rho and conversely. So, if you want to classify representations of G, it's the same thing as classifying finite terms representations. Oh, rho dot. So, classify finite terms representations. Or C, we always assume, is same as classifying representations of the Lie algebra G. We are always looking at the complex vector space. Now, when you use a lot of complex vector spaces, it's the same thing as classifying.
So, Raghunathan, we need simply connected also for this side.
Sorry?
We also need simply connected for this side.
Can you? My hearing is not so good.
Yes, simply connected.
Well, okay, you're right. I'm sorry. I should. Okay, at this point, let me. Rho dot determines rho is clear. Right. Yeah, if you know it's rho dot, you know it is the differential of representation of the Lie group, then it determines rho because we know what happens to the exponential returning element.
The conversely part would not know.
Conversely, rho determines rho dot is obvious. If you have a representation of the group, of course, it gives you the representation of the algebra by differentiating. The point is, when I say rho determines rho dot, I am assuming. When I say rho dot, I am assuming it is the representation induced by some rho. What I am saying is that if rho and rho prime are such that rho dot is equal to rho prime dot, then rho and rho prime are equal. No matter whether the group is simply connected or not. This is so. What happens is you cannot say, well, yeah, but here, sorry, classifying representations. Here, sorry, for this statement it's okay, but this statement, what you point out is right. You should say something. Classifying of G is the same as classifying representations of G, provided if G is simply connected. Thank you, you are right. Well, the problem is that when a group is compact, the simply connected cover may not be compact. If it's a compact simply connected group, the statement is correct. I'll come to that. If G is simply connected, the representations are completely determined by those of the Lie. So classifying finite representation is same as this. Now, let's look at what happens if G is compact. I've already remarked that G is an almost direct product. Compact connected, of course, of a torus, which is the center, identity component to the center, identity connected component of the center. Well, I'll stick to the whole English spelling of center, unlike Deepadra or Mirachik. So, the identity connected component of the center, that's a torus, is a direct part of the center and a compact connected semi-simple equal. It's almost the products. And then one knows further that the, that I gave this a name of a torus, which is a torus C. So that part, and further, if rho is an irreducible representation of G, rho C is scalars. So, if you know the so hence what is what, and rho of G bracket G falls into SLB, the SLB neighborhood, because SLB is the commutator of GLB. So what happens is this: basically, rho is known, rho is determined. And rho is determined by rho restricted to C and rho restricted to bracket G. Separate. So you look at rho restricted to bracket GG, that gives you the representation on V. You can think of what happens is this. This rho restricted to C is a scalar, but rho of C intersection bracket GG is trivial, because what happens is this: taking an element in the intersection, it goes into a scalar. On the other hand, it goes into a commutator, and any commutator has trace as a determinant equal to 1. From that, it follows that this whole thing is going to be this scalar. Well, not quite. I have to be a little more careful. Anyway, never mind. The point is that rho is determined by rho restricted to C and rho restricted to bracket G, which means these two things give you good representation of C cross bracket G. So the original representation gives rise to representation C cross bracket G, which G itself is a quotient of this group by a finite group, finite central group. Set is almost the product of C and bracket G, which means the quotient is a quotient of that. So what happens is that now for C cross bracket GG, you have a good representation. Look at rho restricted to bracket GG and rho restricted to C, and that gives us a representation of C cross bracket GG, but you make the tensor product. You have a representation of C and the representation of bracket GG. Look at, say, the representation of C is one dimensional, and then we form the tensor product with V. It remains the same dimension. In that, we get the representation of the product. Coming from C, it is a character. Coming from bracket GG, it's something you already know. Okay, and of course it factors through, because we know the original representation that of G. It factors through C cross GG mod rho to find finite central group. That's how you get every representation of G. So every representation of G is a combination of representation of bracket GG and the center, and the central torus. So basically, our problem of classifying representations reduces to the case when G is equal to bracket G. And in that case, the group G, again, this is the fact. So the classification problem reduces to the case when G is equal to bracket G. Let me make one remark here. Bracket GG, if I call this G prime, is its own commutator. This kind of thing is proved very in the following fashion. We look at G and partial quotient G by C. And it's clear that bracket GG here, look at this sitting inside here. The bracket GG intersection C, we know is finite. Because as I said, it's almost the product from which it follows that this intersection is finite. And because of that, bracket GG to G by C has finite color, and therefore it's going to be subjective because of dimension considerations, it's going to be subjective. So this is on. This what I want to say, bracket GG to G by C is on. Now, if I look at G by C and look at its commutator is going to be the image of the commutator of G. But we know that bracket GG maps subjectively onto G by C. Bracket GG sitting inside that already maps subjectively onto that. So it follows that the image of bracket GG is same as G by C and it's equal to its own commutator. So bracket GG is its own commutator. I've already told you that bracket GG is a closed subgroup of G. Bracket GG now is shown to be its own commutator because it's a subgroup which maps onto this, so they have the same dimension, the two groups, and the kernel is finite. Because of that, it's going to be equal to its own commutator of bracket GG circle. And the statement, next statement I want, any of this is proof, is the following. If G equal to bracket GG implies G is semi-simple or equivalently, that is, Lie algebra G is semi-simple. One says the group is semi-simple, the Lie algebra is semi-simple. So, the problem of classifying representations of a compact group reduces to problem of classifying the compact connected semi-simple group, which is what we want to embark on. Sorry?
One small thing that you see, rho C is a scalar matrix. See, the thing is, you have to pretend that rho of C intersection some commutator rho of G. G is trivial. So, rho C is a scalar matrix, and the other matrix is
I'm sorry, my hearing is pretty bad. Maybe
no. Okay, let me repeat it. Rho C is a scalar matrix. Okay. C.
I can't go back the other way around. I mean, the point is, these characters go into determinant one. So the intersection elements can go into two simultaneously. That's all that can happen. Scalar, that can happen.
But you can use rho C as
No, I only said that rho is determined by what happens on C and what happens on G. That's all I'm saying.
okay.
You can put these things together. Sometimes there may be some intersection, but that intersection will go into the corresponding intersection. Will go into roots of that's all that happens.
Okay.
These are technical things which can be sorted out fairly easily. So finally, the problem is reduced to representation of semi-simple, compact semi-simple groups, which is what is going to be talked about in the rest of my lectures. And here, the Lie algebra is going to play an important role. So, I'm going from now on, I'm going to assume that G is compact, connected, and semi-simple. And we draw the G, the Lie algebra G, and I also want to introduce the complex implication of G. G is a real Lie algebra, but G is a real group. Note that any complex Lie group which is compact is necessarily abelian. So no way it's going to be semi-simple anyway. So GC, I know this, but G times C over R is denoted GC. This is a complex Lie algebra. And clearly, if you have a representation of G, it extends to a representation of GC. So it's essentially, so you have a representation of G and B, G1, G2, and B, and homomorphisms of B. And all that you have to do is to take an element in GC, an element here, necessarily the form A plus IB, with A, B, and G, and you simply extend rho to rho C by defining rho C of A plus IB, rho dot. Rho is the representation of G, so rho dot is the corresponding. Rho dot C of A plus IB is simply defined as rho dot A plus I times rho dot A. So you get a representation of GC. And now the complex representation of GC can be restricted to G to give a representation of G. So the entire problem now shifts to studying representations of GC, complex representations of G algebra GC. So the problem shifts entirely to this kind. So studying representations of G well reduces to studying representations to put that in inverted commas for the same reason objection raised to my earlier statement. If the group is simply connected, it's perfect. I can remove the inverted commas. But when it's not simply connected, first the representation of the group will give you only that of a simply connected covering of the original group. But you have to then further look at when that representation descends to a covered group, the group G. So what happens is group the representation of GC gives a representation of G itself, and hence I will call it G to that the simply connected cover, which is naturally the group, the same way as that. And one important result due to Hermann Weyl is the following theorem, which says that if G is compact connected symmetry, the fundamental group of G at any point, say identity, is finite. The fundamental group is finite, which implies that the simply connected cover is necessarily compact. Implies, hence, G tilde is compact. So, as far as symmetrical groups are concerned, there is a bijection correspondence representations of simply connected group. Simply connected groups necessarily compact. I am looking at looking like this. I said G is compact, so hence representations of G tilde, which is a compact group, is in bijection correspondence with those of G. And must talk about finite dimension. The bijection corresponds with those of GC of finite dimension. Finite dimension. I cannot say there can be infinite dimensional representations of GC which cannot be referred to the compact group. It's a different story. You do group at all. So at this, as far as compact groups are concerned, we are only interested in finite dimensional representations because of the Peter-White theorem. And there, any finite representation drifts to that of the group simplified, any finite representation the real algebra drifts to the. And the condition that it's simply connected is not so serious because the group is compact and semi-simple, its universal recovery is also compact. So when you want to analyze representations of G, first analyze representations of G theta, then look for those which are trivial on the kernel of the map from G theta to G. So the essential classification problem shifts to doing it for complex semi-simple algebras. Finite dimensional complex semi-simple algebras. There is a theorem which goes in the other direction, which the following, which is again it says if G is a semi-simple GC is a semi-simple algebra, there is a unique isomorphism real Lie subalgebra G over R such that the killing form of G is negative definite. And hence the Lie subgroup and hence there is a Lie subgroup of GL of GC which is compact and corresponds to algebra Adam. See, recall that we have a representation of GC in in endomorphisms of GC. This is a algebra in the use of rank operation xy minus yx. So you have homomorphism. This, of course, is a complex algebra, therefore real algebra as well. And you have the subalgebra, which I call G. It will correspond to a certain subgroup here. It's only a real subalgebra, so it will correspond to a real subgroup here. So get real subgroup. This of course is the Lie algebra GLB, GLGC. So this you get a subalgebra of NGC because the adjoint representation incidentally is faithful, it's injective because semi-simple algebra does not have a center. If it has a center, one of the definitions of semi-simple algebra is that it has no abelian ideals, and centers are the abelian ideal. So the center is non-zero, so this representation is faithful, it's injective. So he sits inside here. So it's a subalgebra of this, and by the fundamental theorem of Lie theory, to that subalgebra corresponds to a subgroup. Get subgroups. G here. And the point is the group G turns out to be compact. It's a closed subgroup. It requires some proof. it's closed, and you can prove it's compact because you look at adjoint representation on which works on G. The form, killing form is negative definite. So the group leaves invariant killing positive definite form, positive definite inner product on the G. Because the compact group leaves invariant positive product can be done for reals as well as complex, makes no difference. So this group G is invariant form, it's a closed subgroup, and but then it's a closed subgroup, the orthogonal group, because it leaves invariant this form. It's a closed subgroup, the orthogonal group. The orthogonal group is compact, and therefore this group has to be compact. That's the way one puts it. Okay, and then once it's compact, it's circular is again compact by the theorem of weight, which I now quoted. So what Hermann Weyl proved is that given a given a complex simple algebra, there is a real subalgebra whose group simply and group corresponding to being compact. And therefore, if you take a representation of GC, it gives rise to a representation, what I call G there, and therefore the corresponding compact group. And we know that all representative compact group are completely reducible. Therefore, the same thing is true of the simpleton group, same thing is true of the group of its Lie algebra. All the finite dimensional representations of the corresponding Lie algebra, because the group is simpleton, corresponding Lie algebra, all representations are bilateral correspondence. So the Lie algebra representations are completely reducible. Therefore, the Lie algebra representation GC, the complexification is also completely reducible. So, a priori we know the theorem for Lie algebras, which are Lie algebras of compact semi-simple groups. Now we have proved it for all complex semi-simple algebras. And then you went one step further. You can prove it for all real semi-simple algebras. The idea is start with real semi-simple algebra, complexify, you get a complex semi-simple algebra. So representations of finite representations of the real algebra are completely reducible if only if the complex simplification is true. And for the complex simplification, because of this theorem, it comes from a compact algebra. So there are final theorems that take a real semi-simple algebra, take its complex simplification. That is also the complex simplification of a Lie algebra of a compact semi-simple group. Then simply representation. And therefore, every representation of semi-simple Lie algebra over reals is also completely reducible. And by what is usually called the Lefschetz principle, it's true for any Lie algebra over a field of characters of 0. If it's true for complex numbers, it's true for anything which is characters of 0, you can prove same thing. There's no real difference. So, something here can be defined over any field. You don't, any field of characters of 0. You don't need real or complex numbers. So it makes sense there. Anyway, so now of course there are other theorems other ways of proving, purely algebraic ways of proving this theorem. The algebraic way is due to J.H. Whitehead, who is a central topologist. He strayed into this business and proved the theorem, and it is known as Whitehead's theorem. Actually, he used cohomology for proving these things. And that the Bourbaki book on Lie algebras gives a proof of purely algebraic theorem, but it's an adaptation of Whitehead's proof. It doesn't talk of cohomology. Without talking about cohomology, you can do things, and that's what they do in that book, their book on Lie algebras. Okay, so now that the whole problem now is to discuss what happens to complex semi-simple Lie algebras. Because we've said that there's a complete correspondence between representations of compact semi-simple Lie group and that of a complex semi-simple Lie algebra. Okay. So we have to embark on what happens to the complex semi-simple Lie algebra. but I will still keep the background of compact group intact, as you see the law. Your business will become evident now. So G is a compact group connected, of course, and Gothic G is its real graph, and GC is its complex. Now, fix a maximal torus P in G. We have seen it is maximal abelian. Now, and let us denote by P. We subalgebra of G, which is corresponding to P, and TC will be the C span T is abelian, so is TC. So to abelian. And here is something which again I'm not going to prove, but it turns out this is a characterization of PC. PC is the maximal abelian subalgebra consisting such that add X is the mapping of GC to GC is a diagonalizable endomorphism for every X in PC. Because if you look at the torus T, that acts on the algebra with the adjoint action, and that action, every element is diagonalizable because they act as skew-symmetric endomorphisms and and abelian, and so they cannot be diagonalized. Diagonalize one of them, then the eigenspaces are again stable to that, so finally diagonalize the whole lot. And therefore, the diagonalize TC also, because simply complexified the algebra T. And so, it follows that it's obviously abelian algebra and it's diagonalizable. It's also true, it's maximal among such subalgebras. That requires a little bit of proof. It's a little, slightly, not very difficult, but it's true. Because what we know is that T is the maximal torus in G. From that, you reduce maximal abelian in G. From that, you can very easily deduce it's also maximal abelian in GC. And diagonalizable is clear, all that is true. But you want to say that it's a complete activity that any maximal abelian subalgebra is really conjugate to this by G. So the statement is following. Any maximal abelian subalgebra is diagonalizable such that, and let me give the name subalgebra H, such that add of H is diagonalizable is conjugate to T, C under the subgroup of G and GC under the complex B subgroup of G and GC corresponding to GC. GC is a subalgebra of, no, GC is subalgebra of endomorphism of GC, and therefore there is a corresponding complex group, because the complex real algebra is a corresponding complex group. So you get a subgroup, and that acts on the real algebra by the adjoint action. The inner conjugation acts on the group G, therefore on the real algebra. And what this says is that any subalgebra which is maximally abelian and diagonalizable can be conjugated into this TC, which is the complex relation of a certain total algebra. This is well, once again, this is it requires some proof. The best proof is using some kind of algebra geometry. I won't go into that. I mean, unfortunately, if to get to what I want to really finally say, I have to assume various things. The proofs are much too complicated to give. I mean, they are not. They use techniques of very different kinds. So it's as I said here, what one makes use of is some algebra geometry, and basically something known as the dominant mapping theorem. That kind of thing is used in a proof. Okay. So the theory of finite dimensional representations of compact Lie groups is the same as compact symmetric Lie groups, the same as the theory of finite dimensional representation for complex symmetrical Lie algebra. As I already said, if you have a compact group, take its symmetrical group, take its Lie algebra, its scaling form is going to be negative definite. If you tensor with C, you cannot talk of negative definite after you go to complex numbers, because the binary form of complex numbers, you can only talk of its non-degeneracy. If the original form is negative definite, new form you get is necessarily non-degenerate. So, the new Lie algebra is therefore so simple as a complex Lie algebra. And then the representation, the finite dimensional is complex Lie algebra and the bijective correspondence with representations of the compact simply connected group covering G. So our problem is completely reduced to talking about complex and simple Lie algebras. Nevertheless, and because of this conjugacy business, what happens is that if you take any of this the diagonal thing, then there is a real subalgebra which such that Rx is diagonalizable to reals, which means Rx is going to be we have all real eigenvalues. That's here to look at this TC here and T here, we know that at T has all eigenvalues imaginary. And therefore, for I times at T, which is again a real subalgebra TC, has all eigenvalues real. And if any real algebra H here of this kind as conjugate to TC, so H itself, any H will split into two parts, the real part and the imaginary part of T. Those with totally imaginary eigenvalues and those with real eigenvalues. There will each be real subalgebras and the whole real algebra will be those with imaginary eigenvalues plus those with real eigenvalues. And those with imaginary eigenvalues will be I times those with real eigenvalues and vice versa. So if you break up into any H will also break up into T plus IT. I mean, that kind of decomposition. Anyway, we now from now on work with one fixed T and its complex expression TC. Let me also give a name I times T. I'm going to call this H. It's a real Lie subalgebra. And the point about H is that all its eigenvalues at X are all real. Now, let's start with representation. Rho of GC on a finite dimensional space. We know that it comes from the finite representation of a simply connected compact group of whose linear algebra tensor with C is given linear algebra GC. We know that. Okay. So rho, let me call it. I should call it because I like to speak. Let me call it rho dot. Rho dot comes from representation of a compact group G, compact simply connected group G. Rho of a compact simply connected group. We know this, which implies rho of the torus T consists of diagonal matrices with respect to some basis. Basis of the representation B. The representation is on some vector space 0, so it breaks up into this. Because what happens is it's a region and every element is diagonalizable. You know, any element, every one times representation through a character. And for the torus itself, when you restrict the representation group to the torus, it has to break up into irreducible representation because it is a compact group. And once that means number of characters, which means you get eigenspaces for the torus. It breaks up eigenspaces for the torus, which means that rho T is diagonalizable with respect to suitable basis of 0. Rho T considers diagonal matrix, which implies, of course, rho dot of T consists of diagonal matrices with respect to basis of 0. And implies that, and what is more with, yeah, and same thing is true, rho dot TC and rho dot H, what I call rho dot H, I times VC. And here, in this diagonal values are imaginary, purely imaginary. And here, all the elements are purely real. That's how the whole thing is. Now, it's kind of look at this space H, take a representation of G, restricted to H. Then I know the space has to decompose into eigenspaces for the whole of H. And the eigenspace under rho dot of H. Because I know it happens to rho of T, therefore it happens to rho dot T, and therefore it happens to rho dot H. So it gets applied. The point is, the eigenspaces the full are rho dot H. So the consequence is this: the space 0 decomposes into eigenspaces which I call 0 lambda corresponding to real linear forms corresponding to real linear forms lambda from H The eigenvalues are real and they are all simultaneously diagonalizable, which means in each eigenspace, it will add to, given an element x in H, it will add to some scalar which they call lambda x, and that is the linear form. So that's how so this implies that V rho is a direct sum of V rho lambda running over linear forms of H star. This applies in particular in the adjoint representation. Look at G, which is the space for the adjoint representation, GC, which is same as the reference space V add. This decomposes into some number of, let me put it like the zero eigenspace. Zero eigenspace means what? You look at all x set x and h commute. Bracket h. Any h in capital H in this with anything in zh, the bracket has to be zero. That is it's a centralized reference. H plus the sum which I write as the eigenspace G lambda, G alpha I call that, alpha and phi, where phi is a finite set and a subset of H star, the dual of H. So this is zero eigenspace, and because H is maximum abelian, this equals H. You decompose it in H because here alpha and phi is a finite subset of H star minus zero. The non-zero eigenspace is taken care of. So these are eigenspaces which correspond to non-zero linear forms. ZH is here, everything is coming with H, which is the zero linear form, but that's equal to H. So the whole thing is decomposed as H plus sigma G alpha. These linear forms, alpha and phi, are called the roots of G, GC. From the one, I will not write GC, I will write G. Certain roots are complex linear algebra, which came from the compact linear algebra with this process. I will write GC also, but sometimes I will forget to put the C, so understood I'm talking about GC. P is the set of groups. It's C or H. There are eigenspaces for HC as well, or TC, what I call TC. See, TC is also can come up as a complex computation of H. So I times T, the original complex, you can also think of it as a complex computation of H. So phi is a set of roots of G, that is the non-zero eigenlinear forms for the action of the group of the action of the algebra on itself by a joint action. So phi is a set of roots. Now, and the Rho's representation then we know that V rho, we have seen, decomposes into some subset P lambda. Lambda is some finite set contained in H star. These are eigenspaces corresponding to the linear form lambda, some finite set correspond to lambda. Yeah, V lambda is the eigenspace corresponding to lambda. So we will decompose into sum of eigenspaces. Distinct linear forms will give you distinct eigenspaces. If they are eigen linear forms. And in this case, the lambda, if you call this S rho, are the weights of the representation. So this is the theory now. One defines something. One defines a certain order on the linear forms on the space. One defines an order, and using that order, one can talk of the highest weight in that order. The total. So one describes the total order, so we only talk of the highest weight in that order. And it turns out, to take a representation, the highest weight occurring in that representation completely determines that representation. That is the central theorem about finite dimensional representations are sensibly addressed for complex numbers and therefore for compact groups. So this is the theorem we are after, and then the next point is about that gives a classification of the representation. How to get it? This gives you a description of all possible irreducible representations. And then to know the representation, you have to know the capital. And that means trace rho g is what you have to know for the representation rho. But this trace function is determined once you know it on the lotus. So to get the capital of the representation, which completely determines the representation, you just have to know this function on the lotus, because everything has a conjugate in the lotus, so that's all you have to know. And there is a formula called the wide character formula, which y do, which gives you the character, the formula for the character, for the representation in terms of the highest weight. So that is the theory of N and Y for compact Lie groups. It's a completely satisfactory thing. We'll have the next, how many lectures do we have? 2 or 3? There are 3 lectures, I will do this business. So today I told you what roots and weights are. Okay? And there's more to be said about roots and weights, about the order of that. That will come the next lecture. I have to stop here. Thank you. Any questions? Actually, there is supposed to be a tutorial after that, and questions can be raised there for those who want questions.